Many people ask me how to calculate the slag structure in FactSage. Uh, as you've probably seen some of the paper from the FactSage group, we sometimes show you the bond fraction or the Q species in the slag, and which is calculated from the FactSage. And this information is not shown by default in the FactSage, so I'll show you how to see those kind of information in the Eclipse program. Uh, in FactSage, we are using so-called modified quasi-chemical model to describe the Gibbs energy of the silicate slag. And the key component of this kind of the model, this model, is the considering the structure of the slag. So as you know, in the silicate slag, we have so-called breached oxygen and the broken oxygen and the free oxygen. So for example, if you actually have the SiO2 have the breached oxygen, and then if you are adding CaO, then it can bring in free oxygen, and then by reacting of the free oxygen and the breached oxygen, it can produce the broken oxygen. So in this way, this kind of chemical reaction can mimic the network breaking reaction of SiO2 by addition of CaO to the CaO SiO2 slag. Okay, so this kind of the concept is the consider inside of the quasi-chemical model. In the quasi-chemical model, instead of using this kind of the breached oxygen and free oxygen and broken oxygen directly, we are considering this breached oxygen and Si oxygen Si bond, and then free oxygen as a Ca oxygen Ca bond, and then by reacting these two together, we can produce the broken oxygen as 2 moles of the Ca oxygen Si bond. That kind of the information can be extracted from the quasi-chemical model. So this actually figure show you the calculated bond fraction compared with the experimental data. So for example, this line show you the amount of the breached oxygen change with the addition of CaO, and this is the amount of the broken oxygen change with the addition of the CaO, and this is free oxygen. Okay, and the symbol here is the experimental data. As you can see, the calculated line is very well matched with the experimental data. So this kind of the bond fraction information is the basically two-dimensional information. But in many cases, you want to also calculate this kind of the three-dimensional Q species information. Unfortunately, in the FactSage, we are not providing the Q species information directly, and so you have to use the statistic to calculate three-dimensional Q species information from the two-dimensional bond fraction information. And those statistics, actually mathematical calculation, is shown very well in this paper. So if you are interested to calculate the Q species information from the bond fraction information, please look at this paper. As you know, also I mean, some of you may not actually very well used to the Q species, and Q species basically explained in this actually the schematic diagram. And the Q4 is typically Si, which is connected by the 4 breached oxygen. And Q3 is the among the 4 oxygen, 3 of them is breached oxygen, and 1 of them is the broken oxygen. That we call as the Q3 species. And similarly, we can define Q2, Q1, and Q0. And so this is calculated Q species information from the bond fraction information by using the statistic. Okay, so now let's look at how to then see this kind of the bond fraction information in FactSage. So the bond fraction information can be obtained in the Eclipse program. Okay, so let's try to, for example, select the CaO SiO2 binary system. So I don't need any of this information. Just take FT oxide here and then say okay. And then I'm going to change this in mole because it's more easy to see the variation of Q species with the moles. And then I add very simple system like a CaO, SiO2, And you don't need the initial condition in this case because I want to just see the structure of the CaUSiO2. So if you do this one, and then if you go next, then you can select your slag, for example, and then you can select whatever temperature. So for example, 1600 degrees Celsius, and then at 1 atm. And then I do the thermodynamic calculation. Then you can see the result like this. And when you look at this result, there's the 2 moles of the slag and then 0.5 moles of SiO2, 0.5 mole fraction of CaO, sorry. And then there's the just site fraction and some information. And there's no information about the bond fraction. As I mentioned, the bond fraction information by default it is not shown as an output of the FactSage. So you have to activate new function in the FactSage to see the actual bond fraction. So how you can do it is you can go to the main menu again, and then there's the so-called parameters, and this is kind of advanced the data in the FactSage. So you can manipulate a lot of things, but one of them is here. So as you can see, show the stable phase only or show bond fraction and etc. So show stable phase only. If you click this one, whenever you have a lot of the phase which have the 0 amount, you can eliminate all of them and you can see only the phase which has certain quantity. Okay. And so sometimes when you do the very, very complex chemical reaction, which have the thousands of the phase, if you click this one, you can see the result much briefly, and you can actually check all the stable phase very quickly. And the other actually the function we want to actually use in this case is the show bond fraction. So if you click this one, now you can activate bond fraction calculation, and then say OK. And then if you do the same calculation, let's try the calculation. Now you see there's some additional information here, and this is the information for the bond fraction. Okay, so SiO, this is same as SiOSi, and this is same as the breached oxygen O0 in the classical actually definition. And this Ca oxygen, this is same as the CaOCa, which is same as O2 minus, the free oxygen. And this SiCaOO is the same as broken oxygen, O2 minus, O minus, sorry. Yeah. So if you sum up all this together, it will be, the fraction should be 1. And now the notation is a little bit strange, but this is because we are using so-called quadruplet approximation, but you can assume that this is same as SiOSi, CaOCa, and SiOCa, which is breached oxygen, free oxygen, and the broken oxygen. Okay, and here this 0 is actually the mistake, so you don't have to worry about this one. Okay, so this is the way you can actually see the bond fraction information. Unfortunately, so far up to the A.0, the FactSage program, we cannot extract this information directly as an output here. So when you look at the plot, or when you look at actually the save or printage, there's no actually the way, there's no way to plot this result or extract this information by the Excel file, for example. Okay, so it's a little bit pity, but I'll show you how to extract this information. So now let's go back again. So instead of doing the one calculation, let's try to do the many calculations. So 1 minus A, for example, and then A like this. So I'm changing the amount of the SiO2. I'm changing the mole fraction of SiO2 in this way from 0 to 1. And then click next. You can set, for example, from 0.1 to 0.9 and every 0.1 information. And currently, if you are using the 0, sometimes it makes a crash of the calculation. So I'm just choosing the information from higher than 0 and lower than 1. Okay, at 1600 degrees Celsius, same calculation. And if you do this calculation, now you can see series of the calculation which containing bond fraction information. So as I mentioned before, we cannot take this one out in the plot here, because if you go to the plot result axis, and y-axis, for example. So just move this one. Y-axis. There's no actually there's no place you can actually to take out bond fraction information, unfortunately. Okay, so you cannot use this one. And also same, if you go to the save or print edge, there's no place to know actually the function connecting with this bond fraction information. Okay, so you have to unfortunately use so-called XML. So if I click this one, this XML program can collect all the information. Okay, and now if you go to the, for example, graph here, then you can see that there's the axis here again, so y-axis, and then luckily you can see now the bond fraction information here. Okay, so I'll click bond fraction, and then I click what kind of bond fraction I want to see. So this is slag number 1, slag number 2, and slag number 2 is not actually not forming in this case. So I'm just taking only from the slag number 1 in this case, and then you can also go to the x-axis as alpha, for example. Okay, and then draw it. Then let's just close this one, close this one. Then you can see that there's the bond fraction information here. Okay, so let me just zoom down. So this one is corresponding to the, as you can see, if I click, this is SiCaOO. So this is broken oxygen amount, and this one CaCaOO. So this is free oxygen amount, and this one, if I click, this is SiOO. So this is the breached oxygen amount. So you can extract actually the information as a graph like this, but unfortunately you cannot save this one directly as the data as an Excel file, for example, in the Excel file. And there's the one more trick I can show you here. So if you go down here, and if you go to the edit, okay, no, so if you go to the edit here, and then if you go to the figure file, okay, then you can see all this information. So this is the text file information to draw this kind of the figure behind. Okay, so if you go down, there's all the text file, all the information in terms of text file. So you can see here, this is SI oxygen amount, and this one is x-axis, this is y-axis for the SiOO. So this is composition of the SiO2 basically, and this is bond fraction for the SiOO. So it's breached oxygen amount. And this one, you can see free oxygen amount, and then this one is broken oxygen amount. So if you take this text file, and then if you know how to use actually the Excel, you can actually copy this one into the text file, and then reading in the Excel as a certain actually the regulation, certain rule, you can actually extract this information very quickly. Okay, so this is the only actual recommendation I can give you to extract many data by one shot. Okay, so let's close it. And then also there's I mean, this is the very simple actually binary system, but if you go to the little bit complex system, so for example, let's add additional one like MgO, and let's add just 0.5, okay? And then go next, and let's just take only one calculation, 0.5. So 0.5 CaO, 0.5 SiO2, 0.5 MgO basically. And then if you do the calculation, now you have the much more actually different kinds of the bond fraction information here. So SI and CA, MG, and then SI, MG. So between the SI, and MG, we can see all the combination of the bond between these three species. Okay, so you have to extract the information, and then you have to treat them very carefully in this case, because this is the breached oxygen amount, and both of this one is the free oxygen amount, and both of this one is the broken oxygen amount, And this is also kind of the breached oxygen, the free oxygen amount. So depending on how you want to actually treat the result, you have to actually recombine them as some smaller group, or you have to utilize this full information for the certain application. Okay, so this is show you how to actually calculate the the bond fraction information in phase. And you can actually see also this kind of bond fraction information for the metallic system as well. So let's look at some calculation like this. For example, Fe Si binary system. So I'll take 0.5 moles of this one and 0.5 moles of this one. And then let's go to the data search. So instead of the Ft oxide, I'm going to take Fs steel database. So among the FACSA database, in the Ft light database and Ft oxide database, the liquid metallic solution in these two database is described by using the physicochemical model, so modified physicochemical model. So you can even see bond fraction between the metallic element in the solution by using from these two database. Okay, and also physicochemical model is very well used in the molten salt. So this actually the database Ft salt. If you click this one, and if you do the calculation for the molten salt like chloride and fluoride, you can also see this kind of bond fraction information too. Okay, so let's just click in this case Fs steel database to see the bond fraction information in the metallic system. And then so these two, and then if you go next, now you can see the liquid steel here. And then at 1600 degrees Celsius, let's do the one calculation. And as you can see here, if you actually consider that there's the random mixing between the ion and between the random mixing in this the Fe-Si binary solution, then we can assume that ion-ion bond and Si-Si bond and that ion-Si bond should be 0.25, 0.25, and ion silicon bond will be 0.5. Okay, but if you look at actually this calculation result from FACSA, you can see ion-ion bond fraction is only 0.13, and silicon-silicon is 0.13, and ion silicon is 0.72. So as I mentioned, if you consider random distribution of ion and silicon in the molten alloys, ion silicon bond will be 0.5, but this is much higher than that. So in the physicochemical model, because we are considering the energetic between the bond, so in this case, ion silicon actually have the negative interaction, so there's the more chance to make an ion silicon bond than the random mixing actually the consideration. Okay, random mixing assumption. So that's why this ion silicon bond is higher than 0.5. And this is actually very important also to develop some physical property model for the molten alloys. And we try to utilize this kind of thing, for example, for the molar volume model for the molten alloys. And also we try to utilize this kind of information for some other physical property as well. Okay, so if you want to develop the structure-based physical property model for the molten slag or molten alloys or molten salt, I strongly recommend you to utilize this kind of the bond fraction information from FACSA. Okay, so if you have any further question, you can always contact me. Okay, thank you very much.